Welcome to my screencast in Chapter 2, the chemistry of life. In this screencast we're going to address basic chemistry, its importance to biology, and some basics and basic review of chemistry, atomic structure, and bonding. Chemistry really is the foundation of biology. If the basic building blocks of biology are cells, well, all of the cells are made up of molecular components. So we need to have a basic understanding of how molecules form, under what conditions they're likely to form, and what are the atomic particles and the rules for those atomic particles interacting into forming molecules, and in turn cells, which are the building blocks of all living things. Everything is made of matter. Matter is anything that has mass and takes up space. Matter is made of atoms, and atoms have subatomic particles. They're protons that are positively charged, neutrons which are neutral in charge, and electrons that are negatively charged. This table, as I'm sure you've seen before, the periodic table of the elements, just shows an organization of all of the different types of matter that exist. I think it's about around 94 or so that occur naturally, and then the rest of them have been made in a lab, in a physics lab. But different types of atoms are different elements. So each one of these represents a specific type of atom and a specific type of element. And we won't get into a lot of detail of how this periodic table is set up, but it does organize them by the properties that they exhibit and how they interact with one another. The number here of 25, about 25 chemical elements, that's not so important. What's important is knowing really these big four. These big four make up the vast majority of living matter. C, H, N, and O. Carbon, hydrogen, oxygen, nitrogen. There's some other ones also that make up the most of life or living things, but really we're going to be dealing with in biochemistry carbon, hydrogen, oxygen, and nitrogen. As we move into talking about bonding properties, we want to point out that it's the electrons. To be sure to know that it's the electrons that determine the chemical behavior of an atom. In other words, it's the electrons and how they are configured and how many there are, especially in the valence shell, the outside shell, that determine how an atom is going to react and interact with other atoms. What we see here is called a Bohr model. This is Bohr's model of what an atom looks like. It's really inaccurate, but it's also useful in just showing you how the electrons are configured and how they will behave in their interactions with other atoms to form molecules. So again, it's the effect of the electrons that are going to really determine how individual atoms behave, how they interact with one another, how they are reactive with one another. So on the left we have a sulfur atom, and this sulfur atom has 6 electrons in its valence shell. The magnesium on the right only has 2. So either way, these two examples, they are going to look to fulfill the octet rule to have 8 electrons in their valence shell. They're going to be rather reactive with other elements. This is a small portion of the periodic table of elements, and what I want to show here is that in the same row, the elements actually have the same number of shells, the same number of electron shells, or in a Bohr model, the electron rings. As you move from the left to the right, what you're adding for each different element is you're adding a proton, but you're also adding an electron. The importance of this is that for the mass of an atom, when you add protons, you're definitely changing the mass. The electrons have a negligible effect on the actual mass or the weight of the atom itself. And so what that contributes to is something called the electronegativity of each atom, of each type of element. And as you go from left to right, that electronegativity tends to increase. And electronegativity is basically, pretty roughly, but the electronegativity is the force or the strength at which the nucleus and the protons in the nucleus, how they hug in or attract or pull in all of the electrons. So as you go left to right, you add a larger positive pull from the protons in the nucleus, and even though you're adding an electron, the pull isn't equal. So you increase the force at which those electrons are held in as you go left to right. So again, electronegativity is the attractive force of the nucleus, or what the nucleus exerts on the electrons. And so it allows us, electronegativity allows us to predict whether a molecule will be polar or nonpolar and how it will react with water, which we'll get to later. But electronegativity is going to help us to predict whether a molecule is going to end up being polar or not. So oxygen, for instance, oxygen has a medium electronegativity, so it doesn't pull electrons all the way off hydrogen, whereas something like a chlorine would. A chlorine would be so strong it'd pull electrons right off of the atom. So oxygen forms a polar covalent bond. In other words, it shares them. So we'll get to those types of bonds in a little bit. But electronegativity will tell us whether it is a polar covalent bond, a nonpolar covalent bond, or an ionic bond. Here's a short animation of electronegativity and how it helps determine how different types of bonds form.
An atom attempts to attract electrons toward itself when bonding with another atom. The level of attraction of each atom is called its electronegativity. When sodium and chlorine react, the chlorine atom removes sodium's valence electron and becomes a chloride ion. The less electronegative sodium atom cannot compete for electrons and becomes a sodium ion. The attraction between the ions is an ionic bond. When bonding atoms have nearly equal electronegativities, neither can attract electrons away from the other. In a carbon-sulfur bond, the electron pair is shared almost equally between the two atoms, resulting in a covalent bond. When hydrogen and oxygen react, the more electronegative oxygen atom cannot completely remove an electron from hydrogen. The shared electrons are attracted more to the oxygen than to the hydrogen atom. This unequal sharing is called a polar covalent bond. Polar bonds have a slightly negative and a slightly positive end.
So in bonding, atoms are going to tend to try to get to the octet rule one way or another. So they're either going to try to complete a partially filled shell or empty a partly filled shell. And really, it's kind of whichever is easier or what the interactive atoms are. So down here on the left, what we have is we're showing how one atom can donate or lose an electron to another. That would form an ionic bond or an ionic compound. On the right, we've got a covalent situation where both of the atoms are actually sharing electrons. That way it fulfills the valence shell and the octet rule. So we're going to deal with a handful of different types of bonds in biology, and we'll deal with some weak bonds, which include hydrogen bonds. We'll talk about hydrophilic and hydrophobic interactions, which deal with the water, and we'll touch upon van der Waals forces down the road, but talk about ionic and then the stronger bonds, which are called covalent. And there's two types, whether they are polar or nonpolar covalent bonds. Covalent bonds are really strong because the separate atoms actually share electrons. They share the electrons in order to fulfill each individual octet rule. So both atoms actually are involved in holding on to the electrons, which makes it a very stable molecule. And A lot of gases have covalent bonds, and water itself is covalently bonded as a molecule. Molecules can indeed be formed by multiple covalent bonds, so atoms can actually share more than just one pair of electrons. And the more covalent bonds there are between two atoms, then the stronger they are. So you could have even double covalent bonds and triple bonds. They're very stable and very strong bonds. One type of covalent bond is first a nonpolar covalent bond. This is where the pairs of electrons are shared equally by two atoms. So here, typically hydrocarbons, and this one happens to be the molecule methane. But if we go back to electronegativity, we'll find that carbon and hydrogen have very, very similar electronegativities. Therefore, neither one of them is going to pull the other electrons closer. The carbon is not going to tend to pull the hydrogens in tight. There's not going to be any winner of this tug of war between the two different atoms. So it's a balanced, stable molecule. To contrast a nonpolar covalent bond, we have polar covalent bonds. This happens when a pair of electrons between two atoms are unequally shared. So the example, and the one that we'll come back to again and again, is water, which is H2O, two hydrogens bonded to an oxygen atom. So oxygen, which has a higher electronegativity, actually has a stronger attraction for the hydrogen than the other way around. If you could think about these two atoms, oxygen and hydrogen, even though there's two in water, if you could think about these having a tug of war, well, the oxygen with a higher electronegativity is actually going to pull the hydrogen in tight. If you could imagine a tug of war there, the oxygen wins slightly. What that actually forms is a slight charge or a pull on each side of the molecule. This little symbol means a delta negative and a delta positive. That just means a slight charge or pull on each side of the molecule. So the oxygen side is going to be slightly negative, and the hydrogen sides are going to be slightly positive. And that has huge implications as to the way that water interacts with itself and the way water interacts with other molecules. Arguably, the most important interaction that polar molecule creates is that water attracts to itself. The attraction between the negative oxygen pole and the positive hydrogen pole, there's going to be what's called a hydrogen bond. Hydrogen bond is extremely important in the way that water behaves. So it's relatively weak all by itself, but in a substance like water, in a collection of water, there's going to be tons and tons, that's not a scientific measurement, but there's going to be tons and tons of hydrogen bonds between the millions upon trillions upon greater groups of atom or molecules than that. So there's an additive effect of this hydrogen bonding. So again, it has a huge effect on how water acts with other stuff. As a side note, kind of for us for right now, that hydrogen bond also occurs between other molecules or even within molecules, like within a huge macromolecule like DNA or into proteins. Hydrogen bonding has an implication or has a force which causes proteins to maintain a certain shape. It helps DNA stay together, the two sides of the double helix, and how it twists about itself. It's all about hydrogen bonding. Now, ionic bonds, on the other hand, again, are caused because there are elements that tend to lose electrons or gain electrons in order to have a more stable valence shell. So the cations in an ionic bond are the positively charged ions, and anions are the negatively charged ions. But the bonds between them result from electrical attraction. So positive cations are going to be attracted to an equal negatively charged ion. So an element that loses an electron will end up with a positive charge. An atom that actually gains an electron is going to end up with a net negative charge. Here we have a sodium, perhaps the most common and most familiar ionic compound is sodium chloride. So we have an instance where this essentially has an extra electron. It's not really extra, but only having one electron in the outer shell, it's going to be easily lost. Chlorine, on the other hand, actually has space for one to fulfill its octet rule. Because of that, sodium ions and chloride ions are going to form an ionic bond because of the attraction between the positively charged ion and the negatively charged ion. So lastly, we'll take a look at one more animation describing covalent and ionic bonding within or between atoms, and we will get to next the implications that this has, especially dealing with the properties of water in living things.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has one valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with one valence electron needs one additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still one short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.